every pharmacist in the world face the same problem to determine the dosage of drug needed by the patient for their treatment. So, what is pharmacokinetic? Pharmacokinetic is the study of kinetic of absorption, distribution, metabolism, and excretion of drug and their corresponding pharmacologic, therapeutic, or toxic responses of men and animals. So, meanwhile, compartment models are classical pharmacokinetic processes of drug absorption, distribution, and elimination with little physiologic details. So, in this paperwork, we will discuss the relationship of ODE, ordinary differential equation, with the compartment model and how the compartment model were very important to determine the drug concentration used in the medicine.
Okay, this video will explain about the relationship of the drug concentration in two compartments, which is the concentration in the gastrointestinal tract and also in the blood vessel.
A physiologic system is often described by decomposition into a number of interacting subsystems called compartments. Compartments should not be understood as a physical volume, but rather as a mass of well-mixed, homogeneous material that behaves uniformly. Each compartment may exchange material with other compartments. Compartment models are visualized by diagrams wherein the rectangles symbolize compartments and the arrows represent material exchange. On the previous figure, we get the equations of the model, which are dg over dt equals to ft minus 7gt over 200 gram per minute, and also dB over dt equals to 7gt over 200 gram per minute minus bt over 100 gram per minute.
Okay, so we proceed to the Laplace method, which I said that we have two equations. The first one is equation 1 and equation 2. So we're going to perform the Laplace equation on equation 1 and equation 2. After that, we're going to get GS and Bs by using the initial condition I mentioned just now, which is G equal to 0 and B equal to 0 equal to 0. So after that, we're going to substitute the value of GS into the Bs. So that after that, we will perform the method of partial fraction, because to inverse back the Laplace form, we need to perform this method, because there is no form of that equation we get in a table of Laplace. So we're gonna perform the partial fraction onto that Laplace equation. After that, we will perform the inverse Laplace method in this equation, which is we're gonna get lastly the BT, which is equals to negative 140 Laplace inverse of 1 over S plus 100 plus 40 Laplace inverse of 1 over S plus 7 over 200 and plus 100 Laplace inverse of 1 over S. And then we're going to perform the Laplace inverse on this equation to get the BT. After we perform the inverse Laplace of onto the equation just now, we're going to get the BT, which is the concentration of drug in bloodstream, which is equals to negative 140 E exponent negative 1 over 100 over T 1 over 100 T plus 40 exponent of negative 7 over 200 T plus 100. So this is the equation of the concentration of drug in the bloodstream.
After we get the equation by using the Laplace transform, the graph has been plotted by using the WX Maxima software. Okay, as you can see from the graph, the blue line represents the gastrointestinal tract and the red line represents the bloodstream in the body. So based on the graph, we can see that the relationship between the amount of drug in the bloodstream and amount of drug in the gastrointestinal tract is directly proportional to times in minutes. Okay. As time increases, the amount of drug in both gastrointestinal and bloodstream also increase. So for the gastrointestinal tract, ingestion of drug happen and the drug concentration getting increased rapidly from time equals to 0. So meanwhile, for amount of drug concentration in bloodstream begin to increase rapidly when the time minutes equal to 5 minutes. So as a conclusion, we can say that the amount of drug concentration in gastrointestinal tract and bloodstream increase as time increase.
Okay, to conclude our presentation just now, we can clearly see that this two-compartment system is very important in pharmacist's life in order to determine the amount of the drug within the body or the blood at any given time when the drug passes into two compartments. There are also the other factors that contribute to the amount of the concentration that play a role in this amount. The wrong in the calculation will result in death or will result in any other disease that will. But remember that any particular mistake that we have in order to solve this equation will result in death of the patients. So calculate it carefully. That's all.